Good morning, everyone. Welcome to the second day of the Blockpool bootcamp. We're about to start. Today we have the first session with the Parity team. Passing the floor to my colleague Evgenia to introduce the speakers. Evgenia, the floor is yours.
Thank you, Leonida. Hello to all. My name is Evgenia Kapasa. I am a researcher and PhD candidate in the University of Nicosia. I would like to welcome you all to this presentation, which is about the Parity European project. The aspiration of Parity project is to address the structural inertia of existing distribution grids by delivering a transactive grid and market framework. Parity will go beyond the traditional top-down grid management practices by delivering a unique local flexibility market platform through the seamless integration of IoT and blockchain technologies. But all these parts are going to be presented in detail by my colleagues. Specifically, the director of Hypertech Energy Labs in Greece, Christos Malavazos, is going to provide you an overview of the Parity project, its aim and solutions. Then Guntram Pressmeyer, which is a junior consultant at E7 Energy Innovation Engineering in Austria, is going to discuss with you the Parity local flexibility market model and the proposed market framework for the end users. Afterwards, the Chief Operating Officer of Hive Power in Switzerland, Davide Rivolla, and the Senior Software Architect from Q Technologies in Greece, Panagiotis Andrianopoulos, are going to describe in detail the IoT and blockchain integration approach of Parity. And finally, Stelios Zikos, which is a postdoctoral researcher in CERT, Greece, is going to present you the Parity use cases and pilot sites. Now let's move on with the Parity overview. Christos, please, the floor is yours.
Can you see my screen?
Yes, we can.
Okay, thank you.
Yes.
So, good morning, everyone. Thank you, Evgenia, for the introduction, and thank you all for attending this morning. I will try to give a very brief overview of the basic aspects of the Parity framework and the Parity project, mainly focusing on how blockchain is considered within the Parity scope. So, some basic figures about Parity, just to give you an idea of the dimensions of the project. It's a kind of a large-scale project, around 7 to 8 million euro funding. It has a 42 months duration. It was funded under the topic of Horizon Europe that requested for solutions that focus on problems of the distribution electricity grid. We have 17 partners from 7 countries. We have 4 pilot sites. You'll have the opportunity to see more details later on today, and 2 pre-pilot site areas. Now, what is the problem that we're trying to solve? Distributed small-scale renewables combined with batteries is rapidly spreading as more and more consumers consider this an attractive and cost-effective option. And this is gradually starting to seriously challenge the traditional utilities, both operational, sales, and revenue models. And this grid decentralization trend calls for more distributed and more scalable solutions. And it is this mission to offer such distributed solutions that presents a great opportunity for IoT and blockchain technologies. So, responding to this exact need, Parity will attempt to offer innovative smart grid solutions right at the intersection of IoT and blockchain. It will deliver distributed, automated, self-learning and self-organization capabilities of various grid assets, devices, buildings, districts. IoT-enabled machine-to-machine communication will be further supported and extended in some sense by blockchain-enabled microtransactions. And finally, traditional service-level agreements will be implemented now in the form of rich smart contracts. So, emerging trends for decentralization and digitalization call for the adoption of novel methods, and this seems to be a nice place for IoT and blockchain solutions, which have a perfect mix for such a problem. As far as IoT and AI is concerned, efficient grid management requires assets to react on short response times, something that people cannot physically achieve. And this is the work of machines and systems that can respond to grid requests, acting, however, on behalf of consumers' energy demand. On the other hand, energy demand is mainly driven by human preferences, either in offices or in homes. So this eventually becomes a typical cyber-physical problem. With the use of IoT and digital twin technologies, Parity introduces strong human-in-the-loop considerations into automated control. Overall, IoT offers high degree of field-level interoperability and context awareness. In addition, distributed AI offers strong self-organization features. However, intelligence is not enough by itself to convince consumers to engage in any kind of new forms of energy transactions. Consumers also require reliability, trust, and transparency, and this is what blockchain has to offer. So, different blockchain approaches, of course, have been tested and are being tested in the energy domain, from simple data governance and management of financial ledgers to more advanced optimization energy flow frameworks. Put simply, utilities can benefit from blockchain in major two ways: on the dynamic and cost-reflective energy price formation that rewards and incentivizes flexibility on the side of demand, and on enhanced network management through increased situational awareness and energy flow monitoring. These are two pillars that are both addressed by Parity solutions. Finally, it seems that one goal that both IoT and blockchain share in common is their aim to cut out the middleman, and such a combination can help actually rewire the grid management systems and methods. Now let's have a quick peek into the Parity concept. This is a simplified depiction of a typical distribution grid area. Successful integration of demand flexibility in the energy markets relies on the efficient modeling of very complex domains related both to the physical ecosystem, grids, buildings, assets, and their characteristics, but also in human behavior and energy markets. So it is common belief that current systems, operations, and regulations fail to effectively address all these domains, and this has been proven. So through a multi-protocol gateway, Parity will offer human-centric control. By human-centric, we mean personalized control of critical home and office loads: heating, cooling, hot water, energy storage, both batteries, but also thermal storage, and EVs. The gateways will also be the connection points between the physical ecosystem and the Parity digital twin framework that constitutes a dynamic digital representation of the local grid entities. Furthermore, a blockchain overlay network will be deployed on top of these gateways. Through the blockchain network, prosumers can actively engage in local peer-to-peer transactive energy frameworks. This will offer automated consensus on the optimal energy flows without relying at all on any centralized authority. In addition, Parity will also attempt to gradually incorporate, push, shift IoT features and distributed intelligence to the edges of the blockchain platform, tightening in this way the association between the blockchain market transactions, the IoT digital twin platform, and the physical ecosystem, which should all ideally operate in sync. Finally, different actors like consumers, DSOs, ESCOs, aggregators can engage in flexible service contracts and enjoy different services. Automated and personalized service level agreements like energy performance contracting, heating as a service, etc., at both building and district level will offer direct, flexible, and transparent automated settlements and high levels of servitization, which is the optimal goal. Now, concerning the Parity IoT and blockchain ecosystem, Parity, first of all, will offer an integrated digital twin platform that will continuously analyze wireless sensor network information and coordinate energy assets of different types like PVs or buildings and their assets in order to offer personalized service bundles for varying user preferences like comfort, energy efficiency, self-consumption, self-efficiency. Within Parity, blockchain will be mainly utilized as an enabling technology for streamlining novel but also flexible transactions and information flows. So the Parity blockchain framework will accommodate both peer-to-peer energy trading operations, market operations, as well as non-market related direct transactions like new forms of energy performance contracted services implemented in the form of smart contracts. Overall, blockchain's disrupting potential is concentrated where it can enable a more decentralized functioning of markets or information exchanges whatsoever. So its added value, it seems, lies more into decentralized nature than its mere performance. So at least given today's technologies and their capabilities. And this is how Parity considers blockchain and its challenges. So as already mentioned, Parity will attempt to introduce distributed intelligence and self-organization features to the blockchain platform through streamlining the information flows between the digital twin platform and the blockchain. This will be the responsibility of the Parity Oracle. Deployment-wise, Parity will attempt to offer a single device that will also act as a wireless sensor network bridge, an IoT gateway, and Oracle and a blockchain agent host at the same time. Finally, Parity will allow multiple complex and often competing business services like smart home services, energy performance contracting, or flexibility services to seamlessly coordinate, to coexist, offering this way agility and flexibility to business service providers. Now, enhanced and data-driven SLAs will support innovative and servitized business models. Now, energy and flexibility will be transformed into some kind of electronic asset, kind of a credit that can be dynamically and interoperably exchanged with the use of blockchain in different settings and different scenarios, like flexible credits or neo-retailer models. Transactions and settlements will not be based on mere kilowatt hours, but instead on other intuitive values, more, I would say, appealing to consumers and flexible business models like comfort as a service agreements. Parity follows an agile development approach. Prior to full demonstration and rollout of the Parity solution, Parity will be tested in relevant lab settings like the self NZAP building and the Hypertech IoT lab, and then pre-validated in a relevant operational environment, the Hypertech Living Lab, prior to real-life demonstration and validation in 4 different pilot areas: Greece, Switzerland, Sweden, and Spain. These have varying geographical, political, cultural, regulatory conditions, building typologies, and this enables us to extract valuable conclusions and concerning not only techno-economic aspects, but also marketing and policy reform recommendations addressing these diverse market contexts. Now, overall, consumers and prosumers should be able to receive some kind of tailor-made personalized service bundles and contracts and participate in future business models and market frameworks. This should be possible in an intuitive and a seamless manner by setting their high-level preferences, for example, like I'm more into savings or comfort or green energy, and subsequently their devices abiding to these preferences should be able to automatically connect to local microgrid through secure decentralized platforms that aim to incent devices that act always on behalf of their owners to shift their operational patterns, offer their flexibility based on fine-grained and near real-time signals. And this is more or less of what Parity is all about. Thank you all for your attention. You will have the opportunity to see much more details about the project and the blockchain application later on in the presentation of our colleagues.
Thank you, Christos. Let's now move on to Guntram, which he's going to discuss with us the Parity Local Flexibility Market Model.
Yes, thank you, Evgenia. I will share my screen now. Okay, now you should see my screen. So welcome everyone. Thank you for giving us the opportunity to introduce the Parity project here at this Blockpool Bootcamp, Blockpool Bootcamp, sorry. I will talk now about the local flexibility market model that we're proposing in the project. So, as Christos already mentioned, the idea of the Parity local flexibility market tackles a lot of different aspects. And here I just wanted to pinpoint the most important keywords we're using. But breaking all this down to the core components of the market platform, I would put it like this. Because what we want to do is to create an end-user centric local flexibility market. So the overall goal is to provide flexibility for the distribution system operator. And the distribution system operator, the DSO, needs a certain level of flexibility to avoid congestions and voltage violations in the distribution grid. And in parity, we want to use the flexibility of end users for this purpose. So, for example, using battery storages, EVs, or flexible assets like heat pumps. And finally, we want to activate this flexibility at the end user's premises through price signals and through transactions between the prosumers. So that's the idea in a nutshell. And I would now like to explain to you the market model we're proposing in a more visual way. So starting from scratch, we're talking about local prosumers. So all of these prosumers are connected to the distribution grid. And the distribution grid is run by one dedicated entity, the DSO, who is regulated. So the prosumers need to make a contract with this DSO to enter to get connected to the grid. On the other hand, the prosumers can freely choose their energy supplier. So it could be that each of these prosumers has different suppliers. So that's the starting point for parity. So now we are asking ourselves the question, how can the DSO request this flexibility? And essentially this depends on regulation. Because the DSO is a regulated entity, as I said before. And we are distinguishing two general approaches how this could be implemented in the regulation. And that's on the one hand, an explicit local flexibility market. What does this mean? This means that the DSO is establishing a platform where he procures flexibility in an explicit way. So for example, a marketplace with auctions could be an option here. On the other hand, the next option is what we call an implicit LFM. So here, basically, the DSO is adapting its tariff scheme and is providing a spatial temporarily varying grid tariff. So that's basically a tariff that is dynamic in with regards to time and location. And in this way, the DSO can set price signals reflecting the grid constraints. So these are the two basic options that could be implemented. And now, as I said, we want to activate this flexibility from the prosumers through transactions. So we have the local flexibility market for the DSO, and on the other hand, we then have a local energy market for peer-to-peer trading. So on this peer-to-peer market, the prosumers can freely trade electricity peer-to-peer. And they also can use their flexible assets like heat pumps, like battery storages, to shift loads and therefore optimize their trades on the local energy market. So just one comment on these abbreviations. So we are using the term LEMO for local energy market operator and the term LFMO for local flexibility market operator to distinguish between these two concepts. Now, the next question is how we can create now flexibility for the DSO from these energy transactions between the prosumers. And this can be done again in two ways, depending on if we have an explicit or implicit LFM. If we have an explicit LFM, so this dedicated marketplace, the DSO is placing a request, a flexibility request on the local flexibility marketplace. And the LEMO is making an offer for flexibility on this marketplace. And for activating this flexibility from the prosumers, and that's now a very important step, the LEMO translates the explicit flexibility request into price signals for the prosumers. So this is an important step, how the prosumers can then react to these price signals and therefore create this flexibility. A little bit easier, it's easier in the implicit LFM because here we don't need to translate anything because the DSO is already just placing these price signals towards the prosumers with the grid tariffs. And finally, the trades, the peer-to-peer trades among the prosumers are affected by these price signals, of course. So the prosumers have two price signals in this case, one coming from the local energy market, so demand and supply from the local peers. And on the other hand, the price signal from the DSO reflecting the grid constraints. So that's these are the possibilities how this flexibility can be created from this energy trading. So now we have this local market, but in parity we also aim to create a link with the already existing electricity markets. Because yes, we don't want to have this standalone market. We need to be integrated somehow in the European national electricity markets. And in parity, we consider the aggregator as the entity who is providing this link. So we have an aggregator who is trading on the ancillary services market, which is run by the TSO, or on the wholesale market. And so the aggregator is trading explicit flexibility there on these markets. And in order to trade there, the aggregator is requesting flexibility from other entities, such as the LIMO. So there are many other maybe industrial sites or whatever that can be aggregated from the aggregator, and one such entity that is aggregated by the aggregator can be the LIMO, so the local energy market operator. And this yes, how can we then activate this flexibility again from the prosumers? This is happening in the same way as before. So the LIMO is offering explicit flexibility to the aggregator and activates this flexibility from the prosumers by using price signals. So again, translating this explicit request into price signals for the prosumers to react. So now we have different markets. We have the local market, we have the national markets, and we now need to answer the question, how can we coordinate all these different markets and the different flexibility requests coming from these markets? And for this, we are proposing to use the traffic light approach. So the traffic light is an instrument which indicates the current state of the distribution grid. So if everything is running smoothly or if there are any constraints to be expected. If we're here in this green state, the grid is indeed running smoothly. So there's no need for flexibility for the distribution grid. So here we have the opportunity to freely trade peer-to-peer, and also the aggregator can request flexibility from the LIMO. Yes, as we don't have any problems in the distribution grid, there's no flexibility needed for a DSO. But this changes then in the yellow grid regime, in the yellow grid state. And here the DSO needs flexibility because in the yellow state, the DSO forecasts a certain problem in the distribution grid, for example, a congestion at some node. And again, as I said before, we have the explicit and implicit LFM. In the explicit LFM, this happens through explicit requests on this marketplace, and the peer-to-peer trades are then affected by these translated price signals from the LIMO. But what we are restricting here is that we don't have the participation in other markets through the aggregator. So there are no aggregator requests in the state. That's because the price signals coming from these markets could contradict the DSO needs. So for example, if on the wholesale market the prices are very low and the aggregator wants to buy electricity there, the prosumers also would like to buy a lot of electricity, of course. But this could contradict a price signal coming from the DSO who wants to turn down loads in order to stabilize the grid. So that's why we are excluding here this participation in other markets. Similar, it's in an implicit LFM. We have no requests from the aggregator, and the peer-to-peer trades are affected by the price signals coming from the DSO. So in the red state, finally, the grid is severely in danger, let's say. So there are critical constraints detected by the DSO, and the DSO needs to take direct control. So the DSO controls loads at different nodes at the connections of the prosumers in order to prevent blackout or widespread blackout or a damage at some grid components. And so here the market-based activities end. So concluding all these aspects, this market model from a prosumer perspective, or the perspective of an end user, I want to raise these 3 points here. The users are finally facing price signals, as I said. So on the one hand, from the DSO and the implicit LFM, and from the LIMO, where the LIMO price signals indicate the demand and supply in the local energy market, and also these translated requests from the explicit LFM and other markets. Secondly, the users can then react to these price signals and change their load profile by doing load shifting. And they also can adapt the peer-to-peer energy trades accordingly to this load shifting. And finally, I want to highlight that, of course, all these transactions and this dispatching is not done manually, of course, but automatically. And that's basically why we're here today in this session, because the blockchain can help here a lot to facilitate these transactions. From user perspective, I want to highlight that the users are generally not very price sensitive, but very much comfort sensitive. So the comfort parameters are very important to be maintained, and they should be not affected a lot by these price signals. And finally, at the end users, they really need to understand and they need to see the cost savings on their energy bills, because that's an essential user requirement we identified. So that's basically what we are proposing in the market model for the parity local flexibility market. And I would like to thank you, and now hand over to Davide Rivola from Hive Power, who will talk about more about the IoT and blockchain aspects of parity. Thank you.
Okay, thank you, Guntram. Okay. So now we will focus a bit more on the interaction between IoT and blockchain. So as we saw from the previous presentation, basically we are in the Parity project enabling a local energy sharing that valorizes the energy internally and helps the grid. And this is brings up new business model, as we saw, which are tied to local energy and flexibility market. And in order to do so, I think the important part here is really that the security automation or the operation that we are doing in this very granular and local markets are guaranteed, will be guaranteed by the blockchain technology. So the blockchain technology in this case can be utilized to secure the operation on the automated IoT devices, because the IoT devices can be from multiple sources. There is a lot of aspects also tied to cybersecurity. So there will be a lot of edge algorithms, as Christos says, that will be deployed inside these IoTs. So it will be quite difficult to control everything. So the blockchain technology can allow us to automate the operation, but in a very secure and a secure operation. So in Parity, we saw that all the IoT layer, this Parity Oracle, will be mediated through blockchain and will be utilized by several type of apps from facing to several kind of user, either prosumer, which has their own prosumer apps. They will extract what is actually happening in a very meaningful and very easy way to understand for them. And then also we will be interconnected with other users, which are more B2B, like the aggregator, LFM operator, DSOs, and also higher level of the grid, like ancillary services, wholesale market, selling and buying, and so on. So we really see that all these players, either devices or actual human or corporation, they are all mediated by the parity blockchain. So I leave the word to Panos from Q, that will explain a little bit more in detail how the IoT devices are working, and then we'll go through the blockchain.
Good morning all. Thank you, Davide. Actually, let's start with the lab trial that we executed in the very early phase in the project in order to see how we proceed from the theoretical part to the actual part. So we started with a lab trial scenario that has been designed in order to implement a simple prepaid energy contract scenario in which the IoT actually monitors the energy consumption of a single device and can exchange information both with the blockchain and the IoT ecosystem. In the blockchain, there's a smart contract which decides actually how the billing and the settlement will occur, and decide for further actions such as controlling the device or make decision how this is going to be controlled. So, in a nutshell, the lab trial is composed of IoT gateways, which actually is simple gateways which gathering information, acting also as a blockchain node. So it hosts inside deployed the blockchain nodes of the project. The devices that are measured is either light devices or HVAC devices and smart plugs. And there is the Oracle, which is the mediator in the blockchain and IoT system world, which serving actually as a link between this world. Davide, please, in the next slide, if you want. Thank you. So, the IoT ecosystems consist by IoT gateways, which are deployed on premises, and also consist by information management cloud, which actually hosts the data persistence and is responsible for data processing and making heavy performance, other performance indicators such as power consumption and user comfort preferences. So the gateway is responsible for the communication between the wireless sensor network in-house or in lab and the IoT infrastructure. It is also responsible to communicate with all the self-sensors, which actually aims to serve ambient sensing, control metering, sub-metering data in a wide range of the self-sensors. So all this information is driven to the information management layer, which is a cloud infrastructure, as I already said, making normalization, having a preprocessing of the data, making semantic annotations on the data that arrives from the wireless sensor field layer, and making compression on this data. Davide, next slide, please.
Yes, sir. Yeah.
Thank you. So the blockchain ecosystem actually consists by the Parity Cosmos sidechain, which actually aims to interconnect the Cosmos blockchain, the public blockchain, with the Parity world. So, as you can see in the bottom, there is, let's say, a three-layer architecture, which is the Cosmos blockchain, the Parity Cosmos sidechain, which has been for the Parity purposes. And on top of that, in the application, let's say, layer, is the Parity blockchain agent, which has been developed for the project purposes and hosts the whole logic regarding the market, the smart contracts, the smart contracts, and has all the appropriate interfaces in order to interconnect with the outside world. which will be the off-chain third parties application, etc. Let's move on, Davide.
Yeah.
Thank you. So speaking about the Oracle, which actually are the agent responsible for interfacing, as I said before, between the physical ecosystem, the IoT ecosystem, and the blockchain world. They are responsible for convey and verify the real-world events with secure and trusted manner, as David already mentioned, and also are responsible for triggering smart contract transactions. Apologize. Can you still hear me?
Yes.
Yes, sorry, my screen was blocked. Sorry. Sorry, Davide, can you go on the previous slide?
Okay. Yeah.
So, as I said, the Oracle are responsible for retrieving also anonymized data by the IoT ecosystem and by the blockchain ecosystem regarding smart agreements, smart contract agreements to provide all the performance indicators to the blockchain in order for the smart contracts to be operated as designed. Just for the deployment point of view of Oracle and blockchain world and IoT, both can be hosted in IoT gateways. So this makes it easy to be flexible also on the deployment side of our solution. Next slide, David. Thank you. So for next steps on lab trial scenarios, we have the prepared scenario that already examined and evaluated. So next steps can be the heating as a service scenario, which actually increase the complexity both in IoT and blockchain. So in IoT, we have enhanced performance indicators, not related only to a simple metering value, but also to a complex performance indicator such as flexibility or user comfort preferences and boundaries. And also on the blockchain world, we have enriched smart contracts. There is no smart contract that only check and decide if we will control or not the device. After the heating as a service scenario, we are aiming to examine also the local energy optimization scenario, which actually is an optimization strategies also in a local level, taking into account, let's say, a PV panel or an EV charger. So it aims to have an optimization on such level. And last but not least, we are aiming to examine also the peer-to-peer trading, which is among prosumers and not in a local level, including all the information aspects that we talked about. Thank you very much, Davide. The floor is yours.
Thank you. Thank you, Panos. So as we saw, that blockchain agent, basically it's our access point towards the blockchain. And in this presentation, we focus on the Oracle, which is the IoT devices, but in Parity project, there will be multiple software components, also front facing to the user backend systems that will interact with the blockchain. So in our case, we will have 4 components. The LFM platform, which is handling all the administrative topics, and the off-chain data storage for multiple presentation use cases and so on. There's the DSO toolset with supporting the DSOs for his own role within this local energy market. The aggregator toolset, which allows to provide aggregative flexibility in a local level, but also allows to interconnect our local energy market to the BRP and TSO level. And last but not least, the Oracle, which is the IoT device, which allows the interaction with the IoT devices. And all this data, they go through the agent, which is a very, very compact software package that can be run also in an embedded environment. And it will anonymize the data, because this is super important. We before saving the data in a public blockchain, we need to ensure that the proper anonymization and privacy is preserved. It's always a big trade-off between blockchain is about sharing very openly the data, and but there are also privacy requirements, especially in business applications. And then this data is handled by the smart contracts that we are developing specifically for Parity in order to support all the use cases, which are the local market. There are the KPI preserving for specific comfort level for the user and so on. And what is happening inside the smart contract is supported by a market engine, which is running locally. So it's running in every agent and is interacting continuously with the smart contract. So it's handling all the computational intensive activity, which it's not optimal to put directly in the blockchain application. Let's go a bit further how it works. Basically, the anonymizer will provide the data to our blockchain agent, the part that is interacting with the blockchain. And in our project, we decided to utilize the Cosmos network system. So basically, Cosmos network is based on top of Tendermint consensus system. So basically, they are providing a service where you can build your own blockchain. But it's not a private blockchain because thanks to the Cosmos SDK, because we can create a side chain that will interact with the Cosmos ecosystem. So it's not, even if it's a research project, it's already thought to handle scalability and replicability. So we don't want to make the usual private blockchain in a test net, but we want to build something that in principle could be also provided to the industry. And the Cosmos SDK provides all the basic functionalities and basic modules which are needed for in the interaction. So the EBC protocol that allows interconnection with the Cosmos network, upgrade capability for smart contracts, governance, and so on. And on top of it, we create our own module where all the critical business logics for the market and the other use cases are coded directly as a module, an application, a sidechain application. And then we have supporting external module, which are helping the market to run. We have the local energy market automated market maker mechanism, which is it's coded inside the blockchain application and also the supporting off-chain application. And then we have the implicit LFM pricer, which is providing basically the grid prices which are needed to support the local operation of the market. So we have the energy market, which is providing energy prices, and then we have the LFM market that is providing the grid price. These two components will create the final cost for the users. And then all the data is saved again in a loop inside the blockchain, where it will generate price schemes that all the components like the Oracle, the aggregator toolset, they can consume and use to steer their own loads. And an important point that we are tackling in Parity is the GDPR compliance of our application, because the problem, as I said, the blockchain technology was created. Let's say GDPR was thought for a technology that was existing before the invention of blockchain. So of course, GDPR is not super well suited to support blockchain, because blockchain is about data immutability and decentralization. And GDPR is quite rigid, as we know. And then, so it's really important that, but it's a law, we have to follow that, of course. And we have really to make sure that the personable, identifiable information, how it is managed when we save in the blockchain, especially because deleting information from the blockchain is really difficult, because the blockchain is not made for that. So there are different type of strategies to have a GDPR compliance. First, you can encrypt everything. So all the data is encrypted. Then you can anonymize the data or do a pseudo-anonymization. These three levels, as you see, when it's encrypted, the more we go in encryption and to make everything private, then they will be very, very difficult for the smart contract to be usable and do a really automation, because probably they cannot read the data themselves. So if we encrypt everything to say, oh, we encrypt everything, then it's GDPR compliant, then basically the blockchain will be just a storage of data, which is really not what we want to achieve, because we want to have a very high level of automated behavior for the parity business cases. So as you see, the less privatizes the data, then the GDPR compliance could be trickier. And this is really still a very hot topic. There are a lot of ways to tackle this. A lot of projects say we are GDPR compliant, but what is GDPR compliance in blockchain is still not settled. It's a very, very, very active discussion. What we decided to do in Parity is to go towards a pseudo-anonymization. Basically, what we do is, before saving the data inside the blockchain, we will create basically an anonymous ID which is collected, which is tied to the data which is saved. So we will save the actual power values that we are measuring, but we will not attach an identifiable label who this data is owned by who. So basically, the fact that this data is Bob's data or Ellie's data will not be saved in the blockchain. And this is also enabled to kindly indirectly delete the data, because we can this data, this relationship is saved off-chain, and then if we want to, we can delete the relationship, so we will lose the information with where this data is, who is the owner of this data. So this is a way to achieve GDPR compliance. It's still debatable. There are lots of debate on that, but this allows to have a very highly level of automation in the blockchain, because we will have still the raw data from that that we are metered by the devices, and this with this we can unlock automated behavior. So this is what we want to do in the project. And another the problem we are tackling for the local energy market, it's how to implement this energy market in the blockchain. The usual way is to have like a traditional bid-ask order book, but this is it's quite computational intensive, and there is also a problem with bandwidth. We have to think that with blockchain we have to be very, very attentive, to keep a lot of attention about how much computation is needed, because all the automated behavior that we will code, we will be run parallel in a highly parallel way by all nodes. So it's of course there is an efficiency problem, and so for this reason we decided to use an automated market making mechanism. Basically, instead to have an order book, a traditional order book, we have a system that will calculate the prices. So based on the information we get from the agents, from all the agents, and it will calculate the prices which are fixed, parameterized price curve. And I know this looks like a bit simple and maybe not efficient, but this mechanism is utilized right now in a lot of decentralized finance projects in blockchain, and it's already handling billions of dollars. So it's a really good compromise between performance, the performance and resource usage. And thanks to this, basically we can create dynamic prices that for every time slots in the local market, there will be generated a custom price, which is dynamic for the whole community members. This is something that we designed in the last months, and during next year it will be validated both in simulation and also in pilot in the lab trials. So what the sidechain that we are doing in Parity, it's not alone. It will be interconnected thanks to the Cosmos network. With the Cosmos network, you can have a lot of zones that can be interconnected through apps. And in principle, you can create multiple apps, but of course, there is the official apps made by the Cosmos project. And the advantage of this is that we don't need to reinvent the wheel. Here we are doing a local flexibility market, but we don't want to do to do from scratch everything. So if, like, to give an example, if we want to use payment and the user needs stable coins, need a fiat relationship, there are a lot of stable coins projects that are happening in the Cosmos ecosystem that can provide this feature. Or do we want to integrate some governance aspect? There are other projects that provide this feature. And all of these, they can be interconnected with this EBC, the interconnection blockchain protocol system, that allows that all these projects to interchange data. And this is also very efficient energy-wise, because the Cosmos Hub is using proof of stake. So basically it's not using mining. And also the parity zone will use proof of authority, because it says it's highly coupled with the physical system. So we still have a very trusted physical layer. So we have trusted actors that are validating the blocks. And the question people would ask about, really, why Cosmos and Tendermint? There are multiple projects, and this is could be just a conference for this, because there is a lot of promising projects. And personally, I'm not picking sides. There are also a lot of very interesting things happening in Ethereum. Ethereum 2 will launch in few days, which is super exciting. And there is also Polkadot. The ecosystem Polkadot is really booming a lot. But what why we are using this is because the Tendermint is available now. It works, and it's not vaporware, which is not, we cannot take for granted in the blockchain. There's a lot of projects that are promising a lot, but then when you try to use something, it's not yet available. And the system is quite flexible. It allows to prototype some systems in a private blockchain and then interconnect with the other chains. It's green. We are not using mining. It's interoperable, so we are not limited to our own application. And also it's quite scalable. We have plenty of vertical and horizontal scalability. And to sum up the road ahead, we really see that blockchain is hitting the world. It's happening. It will take years. It's a long journey like internet, but this will happen. But the energy use case is quite hard, because compared to other blockchain use cases where, like in finance money is just imagination, is just what we think this exists. There are things that exist only in our mind. Here we are interacting with the physical world. And the physical world, it's hard. We have smart meters that are smart, but not smart enough to connect directly to the blockchain. That's why we have IoT devices doing this interconnection. The appliances that we're controlling, they are limited. They have a limited interface. Digitalization, then energy is still ongoing, it's not finished. So it's a long journey, but the potential is huge. We really believe that blockchain, it's a really good fit with IoT. They will benefit from each other. And also piloting and experimentation is crucial. So it's really important that a project like Parity, that really brings together domain expert for multiple domain. We need the energy expert, we need business expert, the data expert, and in order to test out these systems and try out in a pilot environment. Okay, I thank you, and I will give the word to Stelios.
Thank you very much, Davide and Panagiotis. It was a very interesting presentation. Stelios, the floor is yours for a quick presentation of the pilot use cases.
Thank you, Evgenia. Good morning from me as well. I will share my screen. I think you should be able to view my screen.
Yes, we can.
So I will present details on the Parity use cases and pilot sites. Regarding the use cases, at first we'll have an overview of the use cases, and then a presentation of selected use cases will be provided. 11 use cases in total will be tested on the pilot sites. The use cases are referring to various scenarios. For example, the first 3 use cases are related to individual and aggregated flexibility estimation, either referring to buildings flexibility or flexibility from electric vehicles. Also, use cases 4 and 5 are focused on peer-to-peer energy and flexibility transactions when the network is in green state. Use cases 6, 7, and 11 are about the smart grid monitoring and control done by the DSO. Use case 8 examines the DSO as a flexibility buyer scenario when the network is in a yellow state, according to the traffic light approach presented earlier. And finally, use cases 9 and 10 are about LFM flexibility provision to TSO or BRP through the aggregator. Now, more details on some of the use cases. Use case 4 is titled as human-centric and contract safeguarding energy and flexibility transactions in LFM on the basis of context-aware flexibility profiles. This use case focuses on the participation of prosumers in peer-to-peer energy and flexibility transactions. DSO defines and monitors the grid conditions, and the peer-to-peer transaction procedure is performed through the blockchain agents. When the provision of the requested and promised flexibility has been verified, the blockchain performs the necessary remuneration and the peer receives credits. Use case 7 is about the provision of ancillary services by STATCOM to TSO for overlay network stability. Here, the market is not employed, and communication is performed between TSO and DSO. Initially, TSO sends a support request to DSO, and DSO then calculates STATCOM set points in order to provide flexibility to TSO. Case 8 is about congestion management by DSO through operation of LFM. Here, DSO through the monitoring detects network as in a yellow state, and then request flexibility in the local flexibility market. Their mapping and recruitment is done through aggregator, and dynamic activation flexibility is done in real time to reduce or eliminate congestion. Use case 9, provision of ancillary services to overlay ancillary service market operated by TSO. Here we have a communication between TSO and aggregator when the network is in grid state, and TSO publishes a call of tenders for balancing, and then automated transactions are performed through smart contract. Finally, use case 11 is about grid management when the network is in red state, using automatic control of distributed there through smart contracts. Here, DSO monitors voltage levels through smart meters, and if a threshold is reached, it sends the red network state signal, and flexibility in the area of the same low voltage line will be used. In this use case, the market is not employed and the smart contracts between DSO aggregator and prosumers are applied. Now, regarding the pilot sites, the parity solution will be demonstrated in 4 pilot sites located in Spain, Greece, Sweden, and Switzerland. Regarding the Greek pilot site, there will be included 1 large commercial building and 40 residential apartments, as well as 3 fuel stations, which include the EV charging points. And the use cases that will be tested in the Greek pilot site will be 5 on total: 1, 2, 3, 4, and 5. Regarding the pilot site in Sweden, here they will be included 48 apartments located in 3 buildings. Equipment included will be EV charger, PV, electric water heaters, and battery storage. Also, an office building is included, and in this as well, it is planned to be installed equipment such as EV charger, PVs, battery storage, and also HVACs and heating system will be included. In this site, 7 different use cases shown here will be tested. In the Spanish pilot, first there will be the Cuerva distribution grid area, and also there will be included some office buildings containing diverse number of equipment. And in this site, almost all use cases will be tested. Finally, in the Swiss pilot site, we will have 18 residential houses and 1 municipality building. And 5 use cases will be tested: 1, 2, 4, 5, and use case 10. Thank you very much for your attention.
Thank you very much, Stelios, and all the presenters also. If there is any question. If no, I would like to thank all my colleagues for presenting the parity project and its status and objectives, aim, vision, and their market potential. Thank you all for your time. Leonidas.
Yep. Thank you, Evgenia. Thank you, everyone. We're ahead 7 minutes from time. The research session has already started.